Okay, so today I'm going to take on 2021 number 3. This is a center mass rotational inertia problem, again with another linear mass density like one that I've done previously from 2018. So we're going to take a look at this one. So the first thing it says is here's our rod. It's a triangular rod, can't really tell that from a two-dimensional drawing. Has a non-uniform linear mass density given by the following equation, and they give me lambda is equal to gamma x squared, and then they give me the value for gamma, and x is the distance from point P at the left end of the rod. Now don't let this scare you that you have all these Greek symbols that you're like, well, I don't know what to do with gamma. They give you the value for gamma here, so it's not as bad as it may seem when you first look at that. So on A, using integral calculus, show that the rotational inertia about an axis perpendicular to the page and through point P is 3/5 ml squared. So again, I like these because they give me the answer of what I'm going to get to. And we'll just see if I have enough room to work this on this without changing to another sheet of paper. So using integral calculus. So I know that integral calculus means they want me to use I is equal to the integral of r squared dm. So we're going to start out, and I said I was going to do this on this, but I think I'll go back to another sheet of paper because it just gives me a little bit more freedom to move and to get this on there. So number 3a, it says using integral calculus. So I know that I is the integral of r squared dm. But I don't have like a singular r or a singular point. But they give me this linear mass density. And they say that it's gamma x squared, but then they give me a value for gamma, which is 3m over L cubed times x squared. Now remember that from the other day I talked about that linear mass density is the same as dm over dx because it's my mass as distributed throughout my length. So dm dx is 3m over L cubed x squared. I can solve this for dm, and I find that dm is 3m over L squared, or excuse me, L cubed x squared dx. This is my substitution for dm here. And I'm going to change r because r is no longer r, it's going to be x, since that's the unit that I'm functioning in here, not r. And then I've got 3m over L cubed times x squared dx. The only thing I have left to do is set my bounds. Now you notice that point P is on the left end of the rod, so my bounds are going to be how much is before that, which would be nothing, to how much is after that, which is all of it, or L. So my bounds will be from 0 to L. Alright, so let's take out the constants. 3m and L are m and L are constants, so I'm going to bring 3m over L cubed out front. We're going to integrate from 0 to L of x squared times x squared, which is x to the 4th with respect to x. Now we just do an integral, so 3m over L cubed times x to the 5th over 5 evaluated from 0 to L. When I plug those in, I get 3m over L cubed times L to the 5th over 5 minus 3m over L cubed times 0 to the 5th over 5. So this one just falls out. Those are 0. L cubed and L to the 5th, so I'm going to get rid of this and make this L squared. And I get 3mL squared over 5. And if I go look, what was it they said I needed to get to? 3/5 ml squared. And I'm there. Okay. So there's how we integrate to that. Now on B, it says determine the horizontal location of the center mass of the rod relative to point P and express all your answers in terms of L. So I want the center of mass. So x, Alright, well, we learned x, as the sum from I equals 1 to n of m sub I, x sub I over m. Okay, and we know that big M is the total mass, and that's a constant. So I could bring that outside and do the sum from I equals 1 to n of m sub I x sub I. But we all know that summations are integrals. So we get 1 over m times the integral. Now, we're going to integrate with x with respect to mass. Okay, this is also, you'll see this in some textbooks as your equation for the center of mass. So that's what we're going to do. So we're going to take that same dm that I solved for up here, and that's going to go in here. So I'm going to use that again to make it where I can integrate, because I can't integrate x with respect to mass. I need to be with respect to x. So I get 1 over m times the integral, and we're going to go from 0 to L, because that's how long our rod is, of x times dm, which is 3m over L cubed x squared dx. Alright, so we're looking kind of ugly at the moment here, but I've got 1 over m outside. This is a constant, so it can come outside. We're going to integrate from 0 to L. X times x squared is x to the third dx. My m's can cancel immediately. I see that. Then I'm going to integrate, so I get 3 over L times the integral of x to the third is x to the fourth over 4, and that's 3 over L cubed, excuse me, evaluated from 0 to L. So I get 3 over L cubed times L to the fourth over 4 minus 3 over L cubed times 0 to the fourth over 4. Again, you know, you could leave this off. We know it's going to be 0. So this has 3 L's down here and 4 up here, so I'm left with 1. So I get 3L over 4. And that is my center of mass of this triangular rod. Okay. Next question, which is a bit simpler than these others. Not a lot of math to do in this. It says, for an axis perpendicular to the page, is the rotational inertia of the rod about point P greater than, less than, or equal to a rotational inertia around the rod's center of mass? So we're comparing, what if I rotate it here versus what if I rotate it, whoops, not in the middle, right here at the center of mass. Okay, well, if I rotate it there, and this is the easiest justification that you can do for this, when I rotate it here, all the mass is out here rotating about. Okay, it's distributed farther away. When I rotate it here, I've got mass that's in closer because I don't do the entire length of the rod on either side. So the inertia at point P will be greater than, because the mass is distributed farther from the axis of rotation. So because that mass is distributed farther from the axis of rotation, that makes it more difficult to spin. And so just the relationship that we know between I's and how the mass is distributed. Okay, now they release the rod in the position shown, and it begins to rotate about a horizontal axis perpendicular to the page and through point P. On the axes below, sketch the torque and the angular velocity as a function of time t. Okay, so we're going to draw a picture of the rod. And we're going to draw the forces acting on it. Not on this axle, because there is a normal or a hinge force there that's holding it. But over here at 3/4 L, that's where the center of mass is. So that's where gravity is. Okay, gravity is the reason this rotates. And remember that torque is RF sine of the angle between them. Here's R, 3/4 L. Here's the force. What's the sine here? Well, it's going to be 90. Now, let's look a little later. So a little later in the game, So here we are at 3/4 L. Gravity's acting like this. Okay, but what happens to the angle? Well, R would be like this, so that angle is going to get smaller. So as it falls, the angle between R and F decreases. So the torque decreases. And this is how I'm going to know what to draw on this thing. So when I start out, I'm at the biggest torque possible. So when we start out, I'm up here at the biggest torque possible. And then what's going to happen as I go? Well, I'm going to get smaller and smaller and smaller and smaller. It is not a linear travel, but it is a decreasing value for the torque. For the next picture, it is omega over time. And I know that torque is equal to I alpha. And alpha is the derivative of velocity with respect to time. So the derivative of velocity with respect to time would be the torque over I. I is constant. Remember that this is the slope, because we know derivatives are slopes. So the slope is going to be torque divided by I. If this is constant, then it's all going to hinge on torque. So in the beginning, I start at nothing. Okay, I start at nothing. But remember, the slope of this line is this. So in the beginning, my slope is big because torque is big. But what happens as I go on? My torque gets smaller and smaller and smaller and heads to zero. So my slope gets smaller and smaller and smaller and heads to zero. And so those are my two graphs that show what this rod does as it is released and as it is falling. Okay, the torque decreases, the angular velocity increases, but at a decreasing rate. All right, as the rod rotates from the horizontal position down to the vertical, is the magnitude of the angular velocity increasing, decreasing, or not changing? Well, we just talked about that. We said that torque is equal to I alpha, and alpha will be torque over I. So as I am falling, as I am headed down in that position, this should be torque. As I'm headed down in that position, my torque is getting smaller. My I is staying constant. But because torque is getting smaller, my angular acceleration will decrease, because torque gets smaller as the angle between R and F decreases. If torque gets smaller, alpha gets smaller. Okay. And lastly, here's the rod in its vertical position. It now has a mass of 3 and a length of 1, so I get some values. They want me to calculate the linear speed as it goes through this. Okay, this fell. And I'm going to use my little catchphrase. It fell from up high to down low. Okay, anytime anything is moving from up high to down low to up high, whichever. So I like energy. Okay, anytime I can apply it, I like it. So in the beginning, I'm going to go ahead and write the K naught plus the U naught equals the K final plus the U final. But in the beginning, we're settled down in at that 0 point, or excuse me, at the end, we're settled down in that 0 point. And at the beginning, our velocity is 0, so the kinetic is 0. So this goes away. So basically, I'm looking at the potential that this thing has is equal to the kinetic it has at the end. Now, potential. How do I measure potential? Well, remember that the center of mass is where all forces seem to act. So here's my center of mass. Okay, then it's going to fall and it's going to end up right here. This distance right here is h. Now if you remember from the parallel axis theorem, we talked about h being from the axis of rotation to the center of mass. That's the same thing, from the axis of rotation to the center of mass, that's h. That's how far my center of mass has fallen when it pivots into this up and down position. So that is my original height. So it's mgh is equal to, and when I finish, that's going to be rotational velocity, so 1/2 I omega squared. So let's plug some stuff in. So the mass is 3, g is 9.8. That height, well, where was this at? That's 3/4 L. So it's going to be 3/4 times the length, which is 1, is equal to 1/2 times the I, which they gave me the I as 3 ml squared over 5. Okay, that was what they gave me, 3 ml squared over 5, times my omega, which remember that v is equal to r omega, and that's what they want to know, the linear speed v. So omega is v over r. So this is going to be v over r, which, what is my r going to be? Well, it's going to be from the axis of rotation up here to the point that I'm talking about, which is all the way down here at the bottom. So it's going to be L, or 1. Okay, be careful of that you don't put 3/4 L there. So now I just multiply. So 27, let's see, 3 times 9.8 times 3 divided by 4 is 22.05 is equal to 0.9 v squared. I divide by 0.9, and then I take the square root, and I find that my velocity is 4.9 meters per second. And that is 2021 set 1, question 3. I think that was the end of it. Let's look and see. Yep. Okay, so 2021 question 3, set 1.